This talk is about automatic workout tracking using support vector machine with frequency feature engineering. Advancement in technology have enabled continuous and real-time monitoring, whether in human activity recognition, structural monitoring, or surveillance applications. The integration of hardware technologies with software advancements in machine learning and artificial intelligence enabled the automatic detection, recognition, and tracking of various data generated from wireless sensor networks. Specifically, the development of personal wireless sensor network applications has expanded into daily activity recognition and various physical activity monitoring, particularly in healthcare, for athletes, in various sports, and personal fitness. In healthcare, such sensors and integration with machine learning have proved to be extremely useful tool, even for understanding physical movements. Now, these sensors could be placed in different locations throughout the body to understand other types of behavioral characteristics. A typical IMU sensor is equipped with 3-axis accelerometer, 3-axis magnetometer, and 3-axis gyroscope sensors. And they could be used for weightlifting. Now, weightlifting is a phenomenal exercise and has numerous benefits for a human body, including increased stamina and strength. And these type of sensors will help to understand what kind of weight exercise that they're working on, the number of sets that they are working on, the number of repetitions, amount of rest time in between each of the sets. And these type of activities are what we plan to recognize through this study. As mentioned earlier, the weightlifting is a phenomenal activity with numerous benefits for human body, including increased energy, stamina, and strength. However, being consistent with working out can be one of the most challenging aspects in exercise. So the activity tracking allows users to track the number of sets, exercises, and rest time as mentioned before. And these benefits would motivate users to closely monitor their workout, attend the gym consistently, and also provide a competition-like mentality that will allow each individual to pursue and continue their exercises. This study investigates the implementation and application of machine learning algorithms for classifying data from sensor modules. The type of exercise that we tracked were bench press, the pull-ups, goblet squats, shoulder press, cable rows, tricep pushdowns, and then also rest periods. So if we look at the system setup, it uses wrist wearable sensors, and this sensor is composed of 9-axis IMU. So as mentioned, accelerometer, gyroscope, and magnetometer. For this study, we are using 50 Hertz for sampling, and the reason for 50 Hertz is according to a study that showed that typically 50 to 250 Hertz is a good range of sampling rate for different sports activities. And since our weightlifting activities are a bit more on the lower motion exercise, we use 50 Hertz for this study. And also another reason, data that we are using to train our models, which were from Microsoft Exercise Recognition and Kaggle Gym Workout data sets, all were also from 50 Hertz. So therefore, we use their data sets for training, and then also use our collected data sets for testing purposes. So this sensor unit had 9 axes IMU, but we are using only the accelerometer data. The reason for that is the study shows that accelerometer data is sufficient, and magnetometer and gyroscopes do not really contribute to providing any additional information in recognizing weightlifting type of exercises. Since the exercise involves simultaneous and synchronized movement of the arms. And so therefore it was decided that only one sensor was needed and could be placed on right wrist. So these type of exercises typically involve like a unique body movements. For example, tricep pushdowns and cable rows, they all produce unique body movement, meaning that the classifier should be able to distinguish between each individual exercises. Now this slide here shows the overall structure of the algorithms. So using the training data and using the application at MATLAB, we train our model and we export the trained model, and using the new data that we collected from each individual would be tested, and which would be the new data that would be seen to the model, and therefore we would be able to recognize different activities that were performed, the total time per exercise was involved in, and then also the number of sets per exercise. The machine learning algorithms that we utilize needs the features extracted and fed to the algorithm. So therefore, once the activities were performed, the data was collected, and we decided on which features to extract. So we are using the time domain features and the frequency domain features. The time domain features were mean, which signifies the relative 3D spatial position in the air. And also we recognized different variance and zero crossing to be crucial component in understanding information in the time domain. So variance and zero crossings also will help identify the movement itself of the arms. Now the frequency features will also signify the movement during the exercise. And in order to detect these movements, what we did was we split our frequency spectrum into different power bands, and specifically 5 different power bands in this case. We further optimized our frequency characteristics to best recognize the different events of interest. So for the algorithms, we used specifically the supervised machine learning algorithms such as decision tree, k-nearest neighbors, naive Bayes, and random forest, along with SVM. Each of the baseline algorithms were used and compared against one another. We identified an algorithm that worked best. In our case, the support vector gave us the highest baseline classification accuracy. Therefore, we further optimizing different parameters along with features to improve the performance of the SVM model. Now, in our study, we used the confusion matrix along with ROC curves as a guidance in measuring the performance of our classifiers. As you can see in this confusion matrix, as an example on the right, you can see that the rest activity was easily identifiable because no significant activity. So feature optimization is a critical aspect of improving the performance of the system. However, the time domain feature parameters could not be easily modified as they involved changing the window size. So what was explored was the combination of extracted time domain features along with frequency features, specifically the band powers of different bands. And this combination along with other parameters were what was optimized. The first feature selection method used 5 power bands, and specifically 5 equal power bands, which meant each of the band were broken down into 5 hertz width. With this feature array and using the iterative process that we described earlier, the overall accuracy obtained was around 92% with the SVM model. To achieve this result, variance, power band 1, 2, 3, 4, 5, along with mean values and number of zero crossings were used. In our initial study, what we learned was that higher bands did not really present any discriminating information. So therefore, power band 4 and power band 5 were removed, along with features such as power band 1, which consists of frequency ranges from 0.5 hertz to 5 hertz, did not have too much discriminative characteristics either. And the reason for this was relatively the energy in this power band was very high, and we are only observing the sum of the power within that power band. It did not really provide distinctive measures. So therefore, what we did was we removed the high frequency, and then we also subdivided power band 1 into several different segments, and so which showed a little bit higher performance improvements. What we did initially also was we removed the transitions between activities there, because we thought that these transitions will actually negatively affect the model, because sometimes they could be labeled as an activity, whereas in other cases they could be labeled as rest periods. So the transitions could cause confusion to the model. So therefore we removed it, but as you can see, it did not perform as well as we had expected. Some of them were actually doing well, but these transition regions provide some, cause some confusions. So therefore what we did was we added the transitions back into the classification for training, and again we further split the low frequency bands into several different bands, where power band 1 was 0.5 hertz, power band 2 1 hertz, and power band 3 band power from 1.5 hertz. From power band 4 consists of 2 to 4 hertz information, and band power 5 consists information from 4.5 to 15 hertz. With this type of band adjustments, then we were able to improve our classifier results, and it was performing better in the transition regions as well. Now with this information, we are also able to recognize the duration of each of these activities as well. Now the next experiment that we performed was analyzing a long sequence test data. So when this model was tested with a new long sequence test data, it did not perform as well as it did with the validation set described in the previous slide. Many misclassification again occurred, with several instances of one exercise being misclassified as another. This was likely due to the difference in daily workout activity, which can vary from user to user, and specifically when using an accelerometer, if the rate or the speed of the exercise differs from one user to another user, or even within a user, if it varied from one day to another day, then it could cause this type of confusion. But one positive thing to note is that the activities do overlap closely, as you can see in the figure. And so as you can see here, there are certain confusions, but the predictive classifier output overlaps with the actual classification. So this actually is a good thing. So with this observation in mind, the solution to obtain a clean output from this type of garbled output in the figure was done by post-processing the output. And we call this post-prediction data processing. So post-processing allowed us to gain a much better results. And this was done by making several assumptions about how the data was taken. One of the assumptions was that there was rest time between each working set. As people work out, they will go through maybe 10 sets of an exercise, and then they would rest. They would go through 10 sets of exercise again, and they would rest, and then they would repeat this for like 10 sets or 3 sets, as you can see here. So it is safe to assume that there is a rest period between each of these exercises. And then also another assumption that we applied was that the exercise could not be switched in the middle of a set because it uses different type of equipments to perform these type of exercises. So using this type of assumptions, essentially what we can apply is some sort of smoothing in terms of classifier output and post-processing. That it would be equivalent to a majority voting. So if a set consists of like 50 classification of shoulder presses and 35 classifications of bench presses, then the entire set would be classified as a shoulder press in between the rest periods. So this will allow us to provide smoother output, and which is equivalent to removing noises in a classifier outputs. So this type of post-processing allowed us to obtain 96.3% activity recognition accuracy. So this is a big jump from 92% to high 90s for activity recognition. And so as mentioned before, we are also able to extract the duration of the activity and the number of set tracking as well. So the time tracking can be performed because the sampling rate that we are using is at 50 Hertz. Therefore, that each of the window size, which is 100 samples per window, which is actually 2 seconds, but because the window is overlapping by 50%, so we do know that each feature or each row of features would correspond to 1 second of information. So summing up these predicted outputs, we are able to detect time tracking as well. And also after smoothing or prediction, we are also able to detect number of sets that the subject has performed as well. And we are also able to recognize the average time per set as well. So here's the results for recognizing these type of information. So as you can see in the shoulder press, true number of sets that were performed was 3, but because of these misclassification, the actual predicted set was 28. But after smoothing or after the majority voting, the shoulder press, the system detected was 4. Try push down 3 to 16 to 3, and 3 to 12 was correctly identified as 3 sets, and then pull-ups again to 3, goblets 2, cable rows 2, bench presses was 2. So therefore, there was an error in the shoulder press, and then there was an error in the bench press. But other than that, as you can see here, the predicted sets are now very close to the sets. And then also for activity time tracking, as you can see here, predicted time varies a lot, but after smoothing or after post-processing, now we are able to match the duration much closer than the previous case. So in conclusion, that we can identify that different sets and different activity recognition was possible due to different feature engineering and then also post-processing as well. With the post-processing, we were able to perform or identify these type of different errors to a system where we were able to track these activities much better than previously. So we can say that the classifier not only improved the classification results, but it is also it became more robust to the classifier output errors as well. And for the future work, plan on putting another sensor on the opposite wrist, and that will allow us to synchronously observe the exercise that was performed and gather more testing data from various users to account for more variations. And then also longer periods of exercises in our data sets performed during the gym workout routines. And lastly, we could also perform additional adaptive adjustments for each specific user, such that the user's additional or different routines and adapt that into classifier performance. Thank you very much for listening to our talk.